4.1, 4.2, 4.3, 4.3, number 11. Okay, it says, so we have to do everything including graph, okay? So then we have f of x, x to the fourth, minus 2x squared plus 3. Is this the problem? Am I correct? Okay, very good. So let's suppose we are asked to do everything for this. Okay? So where do I start? I was at the conference today. It was a very nice conference. I really enjoyed it. It was on online teaching, and I learned a lot of new things and new tricks and new things, how to involve my students and how to engage my students, how to communicate. It was a very nice conference. Okay, so first I have to start with the domain, correct? Okay, what is the domain of this function? Yes. How do I know it's all real numbers? Very good, excellent. So negative infinity to infinity. Then I focus on the function first. Obviously, I need the limits, and I need the x and y intercepts. Okay, so I have to write limit as x approaches negative infinity from x to the fourth minus 2x squared plus 3. I started at yes. And what do I write? To the fourth power.
Oh, I'm sorry.
Very good. Then I have to write limit as x approaches infinity from x to the fourth minus 2x squared plus 3. Very good. Excellent. So we determine the limits. We know the end behavior. Perfect. Now the next step is x and y intercepts. So for the y-intercept, that's easy. I have to find f of 0, correct? And that is 3. So 0 and 3. Now for the x-intercepts, what do I have to find? So exactly. So I have to solve the equation f of x equals 0. So I have to find the x-intercepts or the zeros of the function, right? Okay, so then I have x to the fourth minus 2x squared plus 3 equals 0. This, if you remember, is not a quadratic equation. What is the degree? How many solutions do I have to write? 4, correct. So it's not quadratic, but it's quadratic in form. Meaning, if I notice that this can be denoted by, give me a letter except x. T. My z looks very weird, so I'd rather not. Okay, and I notice that if I call this t, or I say let t be x squared, then this is exactly. That's why it means quadratic in form. I can replace it by a quadratic equation, t squared minus 2t plus 3 equals 0. And solve this equation for t. However, this is not factorable, so I have to use the quadratic formula.
I'm sorry. How did you get t squared minus 2t squared?
If I let x squared be t, then x to the fourth is t squared.
Wow.
Because if you square x squared, you get x to the fourth. So if I cannot do this, then it's not quadratic in form. And I have to use other methods to solve.
What other methods could you use?
Newton's method. I can solve any equation for anything. Now, I know Newton's method. I have x minus f of x over f prime of x, put it in the calculator, but I have to use the intermediate value theorem to find those intervals where the solutions are.
Gotcha.
But this one is easier because it's quadratic in form, and this I can apply the quadratic formula on. Very good question, both of you. Very good questions. So then t equals negative b plus or minus the square root of b squared minus 4ac, 4 times 3 is 12, over 2a. Not real. It turns out that the equation has no x-intercepts. 4 minus 12 is not a real number. So since it starts at positive infinity and goes back to positive infinity, this function never touches the x-axis. It crosses the y-axis, but it never touches the x-axis. It will never be a negative number, ever. It will not even be 0, ever. Good? Clear? Perfect. So no x-intercepts. No x-intercepts. I don't know why I have an n in there. Sorry about that. Very good. Good. So then I move on. There is nothing else. I move on to the first derivative. So I find the first derivative first. So this is 4x to the third minus 4x. Are we okay with that? Good. I will definitely factor out 4x, and I have x squared minus 1. I continue factoring, and I get x plus 1, x minus 1. There are no critical numbers coming from f prime being undefined because this is polynomial is defined everywhere. Agreed? But there are 3 critical numbers, right? So if I set the first derivative equal to 0, I get x equals 0, x equals 1, x equals negative 1. Agreed? I go back to my chart. Now I try to study the sign. You can use a chart, like I like to use a chart, or just plug in a number, negative 5. This is negative, this is negative, this is negative. 3 negatives. Negative 0.5. This is why I don't like plugging in numbers, because I have to plug in negative 0.5. So negative, positive, negative. So it's positive. 0.5, positive, positive, negative. 10, positive, positive, positive. I have to determine this value. I have to determine this value. When I plug in negative 1, I have 1 minus 2 is negative 1, negative 1 plus 3, 2. And this function is symmetric. You can write that f of negative x is definitely f of x. It's not going to make any difference if I plug in negative x to the fourth, negative x squared, the function will not change. So if this is positive 2, this must be positive 2 as well, because the function is even. Good. Now this is the moment of truth. These two have to work well together. If they don't, I'll say oops and go back and correct my mistake. Ready? From positive infinity to 2, definitely decreasing. From 2 to 3, definitely increasing. Yes. From 3 to 2, definitely decreasing. From 2 to infinity, definitely increasing. Okay. Now I have to look at the second derivative. This is what I am going to differentiate, correct? Not all this, this. So the second derivative is 12x squared minus 4. I set this equal to 0. So I have 12x squared minus 4 equals 0, or x squared 4 over 12, 1/3. And I have to take the square root. If I forget this plus or minus, I'm in trouble. So I'm going to check and see what this is. What is
0.577?
I had a calculator. Okay, thank you. I just was hoping I didn't lose it. So how much is it?
Approximately 0.577.
So this one, 0.57? Very good, excellent. So there is a negative 0.577 and a positive 0.577, 0 here, 0 here. Now I study the sign of this. It's quadratic. It has a positive leading coefficient. It must be positive outside and negative inside. But you can plug in a number if you want. If you plug in 0, you'll see it's negative. And outside will be positive. Plug in any number you want, and you'll see that. Okay. Now I have to identify max, min, and inflection points. And now I'm ready. After that, I'm ready to graph. What type of point is -1, 2? It opens upward. And the first, if you want to use a second derivative test, I'm refreshing your memory on that. You don't have to. But if the function opens upward, and this is a critical number, -1, and the ordered pair is -1, 2, what type of point can that be? Yes, local min. Now here, the function opens downward, and there is a critical number, and the ordered pair is 0, 3. What type of point would that be? Yes. Now the function opens upward, and there is a critical number, and the ordered pair is 1, 2. What type of point will that be? Or you think in terms of the first derivative, decreasing 0 and increasing. So this is a local max. Everyone okay with this? Tony? Ian? Oh, I wrote max, but I meant min. Of course. Everything okay? Okay, so now we're ready to graph this. Here's the graph. I don't need anything. I only need my chart. I summarize all the information here. Ready? I plot -1, 2. -1, 2. I plot 0, 3. I plot 1, 2. I have to plot, I forgot to determine these values. So I have to go back and plug them in the function. So the function is x to the 4th, x to the 4th minus 2x squared and plus 3. And of course, I have to do this again. And I'm plugging in -1 divided by 3 divided. Please divide it by 3 to power 1/2. And when I plug in the other one, I have to get the same number, 2.44. So 2.44, 2.44. Function is even. So at -0.57, somewhere here, 2.44, so this is 2.44, and 2.44. Ready? So the function is coming from positive infinity, decreasing, opening upward, till this point of local minimum. Is this clear so far? Now it's increasing to 2.44, opening upward, where it has an inflection point. Then here it changes concavity. It continues to increase to 0, 3, but opening downward. And the rest I copy because it's an even function. I don't have to look at the chart anymore. So this is the graph of x to the 4th minus 2x squared. So this is f of x. X to the 4th minus 2x squared plus 3. Very good question. Is this clear? Is this okay? Everyone? Any questions on this problem or the next problem? Anything else you tried? Anything else you have questions on?
27 in the same section.
Yes.
I was confused. In the back of the answer, that
Yes.
was what it had two answers.
Yeah.
I was wondering if it had, does it have to have two?
Okay, let's take a look. I have no idea. So 27 on the same page?
Yeah.
Okay. So let's copy the problem first. So we are given a bunch of things, like we had yesterday, right? Something similar to that. And here they are. So you said 27 on 298. Here it is. F prime is greater than 0 if the absolute value of x less than 2. F prime is less than 0 if the absolute value of x is greater than 2. F prime of -2 is 0. Then limit of the absolute value of prime of x when x approaches 2 is infinity. And the other one is, last one, greater than 0 if x is not 0, x is not 2. Okay, did I copy only from one problem?
Yeah.
Just making sure. Yes, do I have to check or is this it? Okay. Very good.
So can I do something to chart?
You have to make a chart. I shouldn't say you have to, it's highly recommended. But first I have to discuss this. First, before I even look at the chart, this is not clear yet. So I have to solve this, and I have to solve this. And then I'll start working on the chart. So when I'm told the absolute value of x is less than 2, what does that mean in terms of x? Where is the interval? So let's talk about this, okay? When we are told that x is less than, in absolute value of x is less than 2, this really means, in plain English, find x values such that, what does the absolute value of x mean? What is the definition of the absolute value? What does it mean in plain English? Not a mathematical definition, but just in plain English. What does it mean? Distance from 0. Very good. So the distance between x and 0. Okay, perfect. So find x value such that the distance between, which is the absolute value, x and 0 is less than 2 units. I know it's long, but this is what it means. When we're asked to solve the inequality, the absolute value of x less than 2, we are asked to find values of x whose distance from 0 is less than 2 units. -2 and 2 are exactly 2 units away from 0. Where will I find numbers with distance from 0 less than 2 units? In between or outside? Exactly, that's the answer. So then this translates into this and nothing else. This is the translation. So the first inequality is really telling us that x is in the interval -2 to 2. In the same way, what does the second inequality say? It cannot say this. This is taken already. It can say only what? Outside, not infinity. Greater than 2 or less than -2. Numbers that are whose distance from 0 is more than 2 units. You cannot include this. This is taken by a different inequality. So the solution to this is to the left of -2, or, which is union, to the right of 2. Okay? So this one has two different separated inequalities as solutions. X greater than 2, x less than -2. So now I can start my chart, because now I know what is this talking about. Okay, ready? Okay, so I have -infinity. I definitely have -2. I definitely have 2, and I definitely have infinity. Notice that there is no indication about 2 or -2. What does that mean is that the first derivative does not exist at -2 and 2. That's what I see it here. Unless I have some more information, and I do. It says f prime of -2 is 0. So right now I can assume that this is taken care of. Now I can assume that only at 2 the derivative doesn't exist. And I see something else here. The limit as x approaches 2 from either side of the absolute value of the first derivative is infinity. Okay, so if the limit of the first derivative from either side is 2, but it's infinity, what does that mean about the function? What can you always say? I'm sorry? I would say that. It's a vertical asymptote. Okay, so something happens here, right? So I will say, right? It doesn't say that the function is undefined there. It only says that the limit of f prime of x as x approaches 2 from either side is infinity. Okay. So let's put this in. The first derivative is positive between -2 and 2. And it's negative. So there is some sort of contradiction here, but it's the absolute value. So I have a question here. So I'm going to talk about this in a minute. So there is a question mark. On this side, it's okay. But how can it go to positive infinity but be all negative on the other side of 2? So we'll have to discuss this. Okay, so these two are in. Now let's see the last one. So the second derivative, this is what I have here. The second derivative, it says, is positive if x is not 2. Okay, so clearly, this is what it means. It says the second derivative is always positive as long as x is not 2. So at x equals 2, it does not exist, so the function opens up all the time. Okay. So now we have to discuss this. So I have to come back to this before we graph it. Everything else is clear. So obviously the first derivative, or the function, has a critical number at -2 because the derivative is at -2 is 0. So there must be a critical number. It could be that this is a cusp, right? It doesn't have to be a max or a min, right? So it could be a cusp. And actually, it cannot be a cusp because a cusp will be undefined. So f prime of -2 will be undefined. So it cannot be a cusp. So this is definitely a local minimum. So whatever that is, we can put any number we want. So the function is decreasing, and then the function is increasing. Now here, the first derivative is less than 0, so the function must be decreasing, but opening upward. So the only discussion or the only question we have is at 2. Everything else is clear. Okay? First derivative at -2 is 0. So I can put any number I want. This is no information given there. So it's up to us what we want to do. So now let's take a look. Okay. So the function is decreasing to -2 something. I'm going to put it -2, 2. Opening upward is decreasing. At this value, it could be completely undefined. I don't know, or it could be undefined, and this is infinity. It cannot be undefined because it's infinity. So if the whole thing is undefined, then the limit is dne. So it's not a vertical asymptote. So the function exists at that point. So at 2, the function exists. Okay? So that's a local minimum. It will continue, so this is at 2. It will continue to increase. It's always increasing. So it appears that it has a vertical asymptote. Now, I'm given the first derivative. So that's the in absolute value. So the limit of the first derivative in absolute value. So this side could be negative infinity, because the absolute value of negative infinity will be infinity. So, and the function is always increasing. So one option would be both infinity and negative infinity. So this would be vertical asymptote. Okay, still and decreasing. Okay, decreasing here, increasing, decreasing, opening upward at all times. Any questions on this option? Okay.
You have to draw the vertical.
It's not a vertical asymptote. So I should have not graphed anything there. The function has a cusp. I only wanted to show that it has a vertical tangent. So I should have made it a little bit more acute. But that's not a vertical asymptote. Yes?
How do you know it's a cusp and not a vertical asymptote?
It's because it doesn't say, it doesn't tell us that
See-
it doesn't exist
See,
at actual aspects.
it's only because it's increased. Very good question. See, it never changes concavity. It's a very good question. So a function that changes concavity will have a vertical tangent. So for example, x cubed. I meant to write the cube root of x. So the cube root of x has a vertical tangent, and it changes concavity from opening upward to opening downward. Here I can't, because I'm told that the second derivative is always positive, except for any real number except at x equals 2, where it does not exist. Why does not exist? Because the first derivative doesn't exist at 2. So if the first derivative doesn't exist at 2, the second derivative cannot exist at 2. So, and it has to open up at all times, except here where it doesn't exist. So this is opening upward and this is opening upward. Now, obviously, it makes no sense for this to be positive infinity when the derivative is always decreasing. When the derivative is always negative. I can't put positive infinity here. That's why I'm given the absolute value. Just to confuse us a little bit. But once I am told that this first derivative to the right-hand side of 2 is negative, there is no way I can have a positive infinity here, and then all of a sudden, positive changes into negative. Does it make sense? Okay, so now your question, Ian, was why they showed two different solutions, or?
So they have one with the vertical asymptote, and they have one without.
So I consider that this is the best option. If they consider a vertical asymptote, then they consider that the function does not exist here.
So my question, is it possible for us to safely assume that because it says that in f double prime of x is greater than 0, but it's not equal to 2, when x is not equal to 2, and it also says that the limit of x approaches 2 of the absolute value of x.
It's not the absolute value of f of x unless I copied it incorrectly.
No, f prime of x.
Okay.
So because those two are already missing, can we assume that f of x is missing as well?
If you remember, we said that a function has a critical number potentially coming from two sources. One source would be when f prime of x is 0, which I have here. F prime of negative 2 is 0. The function exists at negative 2, and there is a critical number there, which can turn into a max or a min. Also, a function can have critical numbers coming from f prime being undefined, where the function is defined. Okay, if you remember, here's an example. F of x equals the square root of x. The domain of this function is 0 to infinity. But when you determine f prime of x, you have 1 over 2 the square root of x. The domain of this function is 0 to infinity. So x equals 0 is a critical number. But the critical number turns into a max or a min only if the function exists at that point. If the function doesn't exist at that point, then the function cannot have a critical number there because it doesn't exist.
But if it doesn't exist at f prime, if at double prime, could it exist at
So f prime does not exist at 0. F prime does not exist at 0. F double prime will not exist at 0. But the function exists at 0. So when you look at the chart, f prime, f of x, and the second derivative at 0, you have this. Which is a critical number because the first derivative is undefined. So here we are told that f prime at negative 2 is 0. They're not saying that f prime at negative 2 is undefined. Oh, we're talking about 2. I'm sorry. I'm confusing stuff. So I'm told that this is infinity. So the question is, how come that, it can be undefined. If it's undefined, that's the second option. If it's undefined here, then the function does not exist at that point. It will have a vertical asymptote. Okay, so another option would be with this pieces going to infinity on both sides. They can go to opening up, decreasing, still has to be, this is the first derivative, yeah, it works. So we could have a second option in which at -2, I still have the same thing, I don't care about it, right? And then at 2 is a vertical asymptote going this way.
I think, Ian, correct me if I'm wrong, the question was more, given this information that we were given in this problem, how do we tell if it's a vertical asymptote or not?
That's why there are two options.
Okay.
You can't. But you don't have to present both options. In my opinion, if you're given this problem, one option will be enough. Because the problem says, sketch the graph of a function that satisfies all given conditions. You're not asked to explore all possibilities. So they presented two options just to show that the two are possible, but you don't have to show all of them. So I'm happy with one graph, any graph that fulfills all conditions. You don't have to think in terms of if there are 10 different types of problems, you don't have to show different types of graphs, you don't have to show all 10. Because it says a function. Sketch the graph of a function. Just in case somebody thought of presenting the vertical asymptote, then they presented two options. But you don't have to show both options. Good. Next question. Anything else you worked on? If not, I would like to look at a function with a slant asymptote and a function with a hole in the graph and whatever else you want. More optimization problems, anything that you worked on.
Could we maybe do a review of mean value theorem and Rolle's theorem?
Yes. Yes. After or before functions with slant, a function with slant asymptote, a function with a hole in the graph. Before or after?
Do after.
After that? Okay. Very good. So let's look at the following function. I already gave it in the factored form. I just made it up. Already presented in the factored form already, so we don't have to worry about factoring it. Okay, so domain. Yes? -3. Yes? Very good. So at -3, the function is undefined. At 1, the function is undefined. And its derivatives, of course. And at 4. Perfect. What will I have to do next? I notice that there is one factor that goes away, which is x minus 1. That will not be a vertical asymptote. So x equals -3 VA, x equals 4 VA, and x equals 1 whole. If the factor disappears, that can no longer be a vertical asymptote.
said 2, right?
I'm sorry?
The X equals 1 over 2.
A hole in the graph. An open point.
No, I'm saying, what does that say? Oh, a hole.
H-O-L-E. Sorry, my handwriting. So this is x plus 2 divided by x plus 3 times negative x plus 4. Now I need to determine this, and this a lot. And I also have to plug in 0. 0 plus 2 is 2. 0 plus 3 is 3. 0 plus 4 is 4. So 2 divided by 12, 1/6. At x equals negative 2, the function is 0. Where the function has a hole in the graph, when there is a hole in the graph, very easy to determine these. I don't have to write limits. I have to put 1 in here. 1 plus 2 is 3. 1 plus 3 is 4. Negative 1 plus 3 plus 4. So I have to find f of 1, which will be 3 at the top, 4 times 3. So this is 1/4. So this is 1/4 and this is 1/4. So the hole in the graph will be 1, 1/4. Let's determine these limits. 1, 2, 3, 4, 5, 6. Any questions so far? Say it again. Maybe you see something I don't.
No. I was going to ask when you're determining the whole, what you have to do for the x, negative x equals 1, but then I realized.
The f of 1? You're asking about 1/4?
Yeah, got the whole. Right?
So yes, I have to replace in the simplified form, because if I replace it here, I get 0 over 0. So I have to state the restrictions, then simplify, and in the simplified form, I plug in 1. And the two numbers left and right have to be the same. And they are, of course. So I get 1/4 when I plug in 1. Is that okay? Was that the question?
No, because I was just asking because you determined that the whole was at x equals 1. Right?
Because the factor goes away.
Yeah, that's what I was asking.
Yes, the factor in the denominator disappears. It can no longer be a vertical asymptote.
Yeah. So then I realized that the whole can only be there and not at x equals negative 3 and x equals 4.
It cannot be. Those don't disappear, so they have to stay as vertical asymptotes.
So what I was going to ask is why did you do what you just did for x equals negative 3 and x equals 4?
Because if you plug in negative 3, you get something over 0. And you have to find a sign. Yes, very good. Okay, so let's find the limits at infinities first. We know the answer, but I still have to write it. So limit of x plus 2 over x plus 3 times negative x plus 4 as x approaches infinity. And then as x approaches negative infinity. What is the answer? Okay, let's say we don't remember. That's fine. So then limit. I cannot show both, but it's not going to make any difference. That's why I want to put them together.
Infinity should be negative infinity. Negative infinity should be negative.
No, you'll see in a moment why. So I have x plus 2 at the top, and now, although I said always don't multiply the factors in the denominator, if I don't see that, I have to multiply them now. So this will be negative x squared. And then plus 4 and minus 3, which makes it plus x, and plus 12, right? Negative x squared, positive 4x, but minus 3x, and plus 12. So now, I know the top goes to, the sign is not important. As long as it goes to infinity, the sign is no longer important. And the denominator goes to, good. So what do I do in these cases? L'Hopital's rule, very good. What is the derivative of the top? What is the derivative of the denominator? Where does this go now? Exactly. So if you remember, for infinities, when the degree of the top is smaller than the degree of the bottom is much bigger and more powerful, and when x approaches infinity, the function goes to 0. Only when the top has a lower degree than the bottom, and only when we talk about infinities, right? So we know that this is going to be 0, and this is going to be 0. We didn't use positive or negative infinity. So y equals 0 is the horizontal asymptote. Now I need the limits left and right to find the infinities. So limit as x approaches -3 from the left of x plus 2. Now I want this form, not this form. X plus 3, -x plus 4. And then the other limit, as x approaches -3 from the right, x plus 2 over x plus 3, -x plus 4. So -3, oh, I know the numerator is going to be negative, and the denominator is going to be 0. I know that. So -3 from the left is like -3.1, negative, and -3.1 with minus in front, positive 3.1 plus 7, positive. Top negative, bottom negative, the answer is infinity. The top is still negative, the bottom is 0. -3 from the right will be -2.9. -2.9 with minus in front, 2.9 plus 4, positive. Negative over positive, negative. Therefore, infinity, negative infinity. I will repeat for 4. Do we understand this procedure? Yes? Okay, so last one. So limit as x approaches 4 from the left of x plus 2 over x plus 3, -x plus 4. I know the top is positive. -4 from the left, 3.9. Positive. -3.9 plus 4, positive. So the answer is positive infinity. And the last one, x approaches 4 from the right of x plus 2 over x plus 3, -x plus 4. The top is positive, 4 from the right. This will be negative, so it's negative infinity. Because the denominator is negative, but it's 0, but negative on the negative side. So this is negative infinity. Any questions? So now I need to try to find the first derivative and then the second derivative. We don't have, I don't want to spend too much time on this. I will rather just determine the first derivative, see how it looks, and if it's too complicated. I just wanted to illustrate the hole in the graph with this problem. That's what I wanted to illustrate. Okay? So let's now, yes, I want this form, but I will factor out -1 and then differentiate. Okay? So let's just try the first derivative. So it's this. Because there are so many other things that I'd like to review. So derivative. Okay, negative. The top prime is 1. So x squared minus x minus 12 minus x plus 2 multiplied by 2x minus 1. And now I'm going to write the denominator factored. I want it factored into, this time I factored a -1. So it's x minus 4 and x plus 3, correct. Thank you. Good. So then I have minus. I can't factor out anything, so I have to distribute. Squared minus x minus 12 minus 2x squared. This is minus 4x, no, positive 4x minus x, so 3x, negative 3x, negative 2, positive 2. I made up the problem, so that's why it's going to be messy. I didn't do anything before that, no calculation. So this is negative x squared, and this is minus 4x, and this is minus 10 divided by x minus 4, x plus 3. These problems are determined in the book. They're determined so that they are not super okay. So in order to okay, don't forget when we differentiate, the denominator is squared. Okay, so in order to find the critical numbers, I have to set the first derivative equal to 0, which gives us x squared plus 4x plus 10 equals to 0. B squared minus 4ac has no solutions. So this function will never be 0, and lucky me, this function will have only one sign forever, which is only positive. This is x squared plus 4x plus 10. It has a minimum. It never touches the x-axis. It's always above the x-axis. So it's always positive. So I'm happy for that. I don't have to worry about anything. And now I only have to make sure that the first row and the second row work together. Yes, yes, 1/6, 1/4 is bigger than 1/6. Yes, yes. I'm going to give it a shot without the second derivative, or we can try the second derivative. It's going to be messy because I'm going to have to differentiate this 2x plus 4, and then I have to put those in, and then when I get to the second part, minus this times this prime, it's going to take a while. Okay, so I'm going to give it a shot without the second derivative and then check my work. Sometimes it works. Not always. That's one other reason why I put the second derivative last, because I may not be able to find it. It may be too difficult. Okay, so I have negative 3. I have 4. One comma 1/4. It's the open point in the graph. This side, so the horizontal asymptote, that's an overkill. I don't need to write it, but at least remember it's there. So from 0 to infinity on this side, let me use a different color, let's say orange. I don't think there is any problem here. Now, there must be an inflection point somewhere. So first of all, I have negative 2, 0, which is this point. 0, 1/6, which is this point. And then it goes to infinity. There must be an inflection point. It's going to take me a while to find it, but there must be an inflection point. Here's why. The function comes from negative infinity and does this, and then increases here. And there must be somewhere an inflection point because it does this. Right? So it has to open down till a certain moment, and then it has to open down, open up. So I don't know where it is. It may be here, or it may do this. I don't know because I haven't calculated the second. I haven't determined the second derivative, and I didn't set it equal to 0. I don't know, but I don't want to use the time right now. I let you just find the second derivative. And on the other side, it's very clear. There is no inflection point here. I can check with the graphing calculator. but the graphing calculator will not give us the inflection point. We have to go through the excruciating pain of finding the second derivative to find the inflection point. So if you put the graph in there, so remind me what I had. I had x minus 1. Don't forget the extra parenthesis for the top. And then I had x plus 2 in parentheses, close again, and divide by, in parentheses, x minus 1. Then what else we had? X plus 3. Very good. Thank you. Negative x plus 4. Okay? So I'm going to use standard, but I shouldn't really, but let's use standard first just to see the entire thing. Okay, here it comes. There's no problem there. Here's the middle part. Obviously, there must be an inflection point somewhere. I can't determine it. I can't tell you exactly whether it's here. It opens down here, and then it starts all the way up, or if it has the inflection point here, or if it has the inflection point here. I can't really tell. The graphic doesn't even show the hole, but if you go to second and table and you plug in 1, obviously you're going to get an error. There is no discussion about it. Although there is no vertical asymptote there. There is a hole in the graph. So if you go back to the graph, and if you want to zoom in what happens around 1, you can. So I can change the viewing window. I'll say from 0 to 2 for x with a scale of 1. And I want from 0 to 1 because I know. And I just want to see it. There should be a blimp or something at 1. And it is. And you see it. But I had to zoom in so much to see it. Otherwise, the calculator will not show it. I knew it was an error there. But now where the inflection point is, I can't tell. Okay, I'm tempted to say that it's somewhere here. Maybe even here, I'm not sure. I think here, maybe here. See? It opens downward, and at some point in time it changes concavity, so it could be somewhere here. I can't tell. But I didn't want to spend too much time on this problem. I just let you differentiate the second time. Please do that as a practice if you want, and find the inflection point for this function, because we were not able to finish it out. Okay. But it served the purpose of discussing the hole in the graph. Is that clear? Okay. Now, I don't want to forget about Rolle's theorem and the mean value, both or just one?
Whichever you think is applicable.
The mean value theorem, they're both important. So so let's look at an example. In your review, there is no problem there. So
That's why I asked. I think they only saw like one, if any, that were.
yeah, I think they're not. So let's take a look. So these are in section 4.2. Okay, so let's look at problem 3 on page 288. Let's say we have f of x equals the square root of x minus 1/3 x. Forgive me if we did this problem already, or if you have a problem, we can choose that.